Good morning, everyone. I am Jamace Ocio, and I am the third reporter for this group. The previous reporter has already discussed the methods and the steps on how to use the one-way ANOVA F test to evaluate differences among more than two independent groups. However, there are times that factors affect the increase in variability between groups. That is why we have this method that is used to separate the subjects in the sample into subgroups, and within these subgroups, the treatment are then randomized. And this method is called the randomized block design for analysis of variance. So what is a randomized block design? A randomized block design is used to compare treatment means. It evaluates differences among more than two groups that contain matched samples or repeated measures that have been placed in blocks. So when we say blocks, these are heterogeneous sets of items or individuals that have been either matched or have been taken from repeated measurements. So blocking removes as much variability as possible from the random error so that the differences among the groups are more evident. To understand this, we will be using this example. So in this example, there are 20 subjects, 10 are male, and then 10 are females. So what we will do first is that we will take these 20 subjects and then we will separate them into two subgroups. We have the males and the females. So 10 males will be on top and 10 females will be on the bottom. So we do this because there might be some factors that separate the treatment for the males and for the females. So next is we will then randomize the treatment. So treatment 1 will be denoted with blue and treatment 2 will be denoted with red. So when the males are randomized, 5 males are selected for treatment 1 and 5 males are selected for treatment 2. Likewise for the females. When organized with males on top and females on the bottom, we can see that there are 5 subjects in each block. So therefore, it is called a randomized block design. In the randomized block design for the analysis of variance, we partition the total variation for the total sum of squares into 3 variations. That is, we have SST equals SSTR plus SSBL plus SSE, where SST is equal to the total sum of squares, SSTR is the sum of squares due to treatment, SSBL is the sum of squares due to blocks, and SSE is the sum of squares due to random errors. So, the total sum of squares in a one-way randomized block design can be partitioned into 2 parts. The sum of squares within groups reflects variation due to differences in treatments and uncontrolled variation when the same group is tested repeatedly. The sum of squares between groups reflects individual differences. The sum of squares between groups can be partitioned into sum of squares due to treatment and the sum of squares due to blocks. And the degrees of freedom can also be partitioned in the same way. So in the randomized block design, we have the following assumptions. First, the samples are randomly selected. Second, the populations should have approximately equal standard deviation, that is, they are homogeneous. Third, the population distributions are normal. And fourth, population covariances are equal. So let's try to know the procedures in finding the F value for the analysis of variance in the randomized block design. So procedure number 1 is to state the hypothesis. So the null hypothesis will be this one. U sub 1 is equal to U sub 2, which is also equal to, and so on. And our alternative hypothesis will be H sub O is false, or meaning to say at least two means differ. And procedure number 2 is to set up the level of significance. Step number 3 is to calculate the degrees of freedom and determine the critical values of F. So, the first degrees of freedom that we are to find is the degrees of freedom for treatment using the formula C minus 1. And next is the degrees of freedom for blocks, which is equal to R minus 1. The degrees of freedom for error, which is equal to R minus 1 times C minus 1. And lastly, the degrees of freedom for total, which is equal to RC minus 1, where R stands for the number of blocks and C stands for the number of treatments. And to determine the critical values of F, we will refer to the F distribution table, which will be shown on the next slide. So, the F distribution table that we are going to use depends on the level of significance, or on the alpha. So if the alpha is equal to 0.005, then this will be the table that we are going to use. The same goes for the alpha, which is equal to 0.01. Another is for alpha, which is equal to 0.0. Another table for alpha equals 0.5. And lastly, for an alpha, which is equal to 0.10. The next step is to calculate the values of F. So in calculating the values of F, there are also different steps that we have to take. So first one, we have to arrange or complete the table with the data that we are going to need. Second, we will compute the grand mean using this formula. Third, we will compute the x bar sub g using also this formula. And next is to compute the x bar sub I using this formula, where R is equal to the number of blocks, C is the number of treatments, I are the blocks, J are the treatments, x bar sub I is the mean of all values in the block I, and x bar sub j is the mean of all values in the treatment. Next step is to compute the sum of the squares. So we will find the sum of squares for total using also this formula. We also find the sum of squares for due to treatment, sum of squares due to blocks, and sum of squares due to error. So we will be using this formula. So we will be able to understand this formula later if we will be having our example. And also take note that there will be a shortcut formula in finding the sum of squares for error, or SSE, since we already know that our sum of squares total can be partitioned into 3 variations. Then we can derive this formula that SSE is just equal to SST minus SSTR minus SSBL, where SST is again the total sum of squares, SSTR is the sum of squares due to treatment, SSBL is the sum of squares due to blocks, and SSE is the sum of squares due to random. Next step is to compute the mean squares. So for the mean squares, we have this one first. MSTR is equal to SSTR over C minus 1. So MSTR stands for the mean square due to treatment. Next is we will find the mean squares for blocks using this formula SSBL over R minus 1. Next we have MSE equals SSE over. So next is we will find MS. So next is we will find the mean square for error, which is equal to SSE over R minus 1 times C minus 1. Next is we will calculate the values of F. So we have first F sub TR, or the F value for treatment, which is just equal to MSTR over MSE. And F sub BL equals MSBL over MSE, where MSTR is again the mean square for treatment, MSBL is the mean square for blocks, MSE is the mean square for error, F sub TR is the F value for treatment, and F sub BL is the F value for. Step H is to organize the values in the ANOVA table for the randomized block design. So this is how the table for randomized block design looks like. It has 5 columns. We have the source of variations, the sum of squares, the degrees of freedom, the mean squares, and the F values. And then step number 5 is to make the decision. So if the computed F value is less than the critical F value, we will not reject the null hypothesis. But if the computed F value is greater than or equal to the critical F value, then we will reject the null hypothesis. And step number 6, we will state the conclusion depending on the decision. So to further understand this concept, we will try to solve this example. Okay, so a plant manager was interested in the effect of time of day in the productivity of workers in a garments factory. A sample of 5 workers is randomly selected, and the number of garments produced in a given hour is recorded with the following results. So this table shows the number of garments that are produced in a given hour. So there are 4 time periods and there are 5 workers. So using a level of significance of alpha equals 0.05, is there an evidence of difference of average outputs between the time periods? And is there an evidence of difference in the average outputs among the groups of workers? So these are the 2 questions that we have to answer using the steps in the randomized block design for the analysis of variance. So step number 1 is to state the hypothesis. So in the randomized block design, we have to consider 2 hypotheses, one for the treatment and one for the blocks. So for the treatments, the null hypothesis is this one. U sub A is equal to U sub B equal to U sub C and equal to U sub D. Or in other words, there is no evidence of difference in the average output between the time periods. Our alternative hypothesis will be this one. U sub A is not equal to U sub B, not equal to U sub C, and not equal to U sub D. Or there is an evidence of difference in the average output between the time periods. For the hypothesis in the blocks, our null hypothesis will be U sub 1 is equal to U sub 2 equal to U sub 3 equal to U sub 4 and equal to U sub 5. Meaning to say, there is no evidence of a difference in the average outputs among the groups of workers. Our alternative hypothesis will be U sub 1 is not equal to U sub 2, not equal to U sub 3, not equal to U sub 4, and not equal to U sub 5. meaning to say there is an evidence of a difference in the average outputs among the groups of workers. For step number 2, we will set up the level of significance. So, in the given problem, our level of significance, or alpha, is just equal to 0.05. Let's have step number 3. We will determine the degrees of freedom and the critical values of F. So first is that we know that C stands for the number of treatments, and there are 4 treatments, so our C is equal to 4. And R stands for the number of blocks, and then since there are 5 blocks, which stands for the number of workers, so R is equal to 5. So we can now find the degrees of freedom for treatment first. Using the formula, C minus 1 is equal to 4 minus 1, is equal to just equal to 4 minus 1, and so therefore our degrees of freedom for treatment is equal to 3. Next, the degrees of freedom for error using the formula r minus 1 times c minus 1 is equal to 5 minus 1 times 4 minus 1 equals 12. So since we already have the degrees of freedom for treatment and for error, we can now locate the critical value for treatment using the table where our alpha is equal to 0.05. So our degrees of freedom for treatment will be our numerator, and the degrees of freedom for error will be the denominator. So locate first the 3, and here is our 3, and locate then our 12, which is here. So 3 and 12 intersects at 3.49. Therefore, our critical F value for treatment is equal to 3.49. Next, okay, so in this table, we already know that our ground mean is equal to 25.5. So we can now find these values in this column, the values in this column. So in this column, we have x sub a minus grand mean squared, x sub b minus grand mean squared, up to x sub d minus grand mean squared. So to find this, we will just subtract a value of x sub a. So for this one, we have the value of x sub a is 25 minus the grand mean, which is 25.5, and the answer is equal to negative 0.5, and then we will square it, so we have obtained this value 0.25. So the same process for this one. So for this one, we have 12.25. We get this by subtracting 22 minus 25.5 and squaring it, and the answer is equal to 12.25. So all of these values are obtained using the same processes. Now, let's proceed to the next step, which is to compute the x bar sub g's. So again, let us consider this table, or this part of the table, and then when we say x bar sub g's, we are referring to the mean of all the values of x sub a, and then another is the mean for the values of x sub b up to x sub d. So to find first our x bar sub ag, we will just simply add 25, 28, 30, 24, and 21 and divide it by 5. So the answer is equal to 25.26. So the same process will be done to obtain 25.2 for x sub b, 26.4 for c, and 24.8 for d. Okay, so looking at in this table, since we have already found the value of x sub j x bar sub g, we can now find the value of x bar sub j minus grand mean squared. So again, recall that our grand mean is equal to 25.5. So for x bar sub ag is equal to 25.6. So we have 25.6 minus 25.5 squared is equal to 0.01. And the same process for this one, 0.09. We will just subtract 25.2 minus 25.5 and then squared it, and then we will obtain this one. And the same for 0.81 and 0.49. Next step is to compute the x bar sub i's. So we will now consider this part of the table. So our x bar sub I is this one, this column, these values. So for x bar sub I1, that is, we have this row, we will just simply add the values in this row. So we have 25 plus 22 plus 20 plus 25 and divided by the value of c, which is equal to 4. So we will get this 23. And the same value to get 26, we will just simply add 28, 24, 29, and 23 and divided by 4. So we will have 26 up to 25.75. So looking at in this table, since we have already found the value of x sub I, which is written in this column, we can now also find this one. We can now also find this part, these values. So to get these values, we will just simply subtract the x bar sub I value. So we have 23 minus the grand mean, which is equal to 25.5, and then squared, we will get 6.25. The same process for 0.25, we will just simply subtract 25.5 minus 26 and then square. We will have this up to 0.0625. Next is to compute the sum of squares. Next is to compute the sum of the squares. So first is the sum of squares for total. So we will consider this part of the table. So we all know that we have already obtained this one, these values, and then after this we will find its total. So the sum of for this column is equal to 49.25. For this column we have 23.25. For this column we have 69.25, and for this column we have 11.25. So to find the sum of squares, or SST, we will just simply add all these totals. So we have 49.25 plus 23.25 plus 69.25 plus 11.25, and the answer is equal to 153. So that will be our sum of squares for total. Next is the sum of squares due to treatment. So we will be using this formula, or simply we will just consider this table or this part of the table where we have x bar sub j minus grand mean squared. So using these values, we will just add this one. So 0.01 plus 0.09 plus 0.81 plus 0.49, and then multiply it to the value of r, which is equal to 5. So we will obtain this sum of squares due to treatment, which is equal to 7. Next is we will find the sum of squares for blocks, or due to blocks. To make it easy, we will just again consider this table or this part of the table. So to find SSBL, we will just simply add all these values from 6.25 up to 0.0625. So we have this one, 0.0625 up to 0.0625. So we have 6.24 plus 0.25 plus 1.5625 plus 0.25 plus 0.0625, and then multiply it to the value of 4, which is equal to the value of C, which is equal to 4. So our SSBL is equal to 33.50. Lastly, we will find the sum of squares due to random errors, or the SSE. So this will be easy because we have already found the values of SST, SSTR, and SSBL. So we will just simply substitute on the formula. So we have SSE is just equal to 153 minus 7 minus 33.50. And so our SSE is equal to 112.50. Step number 4 again is to compute the mean squares. So for the mean squares due to treatment, we have SSTR over C minus 1. So since our SSTR is equal to 7, we have 7 divided by 4 minus 1, and that is equal to 2.33. Next, we have MSBL using again this formula. So since we have found that the value of SSBL is equal to 33.50, so we will just divide 33.50 divided by 5 minus 1, so we have 8.375. And for our SSE, or our MSE rather, we will just divide SSE divided by R minus 1 times C minus 1, and we will get 9.375. The next step is to calculate now the values of F. So first is the F value for treatment using this formula, MSTR over MSE. And since our MSTR is equal to 2.33 from here, and our MSE is equal to 9.375 from here, so our F sub TR is equal to 0.25, this one. Next is to find the F value for blocks, or F sub BL, using this formula. Since our MSBL is equal to 8.375 here, and then our MSE is equal to 9.375 from here, so our F sub BL is equal to 0.89. We will organize these values in the ANOVA table for randomized block design. So this will be the table with all the values that we have obtained from all the calculations. Now we have step number 5. We will now make the decision. So again, since there are two hypotheses, one for treatment and one for the blocks, so there are also two decisions. First, since the computed F value of 0.25, this is our F sub TR, is less than the critical value of 3.49, so this is obtained from the F distribution table, at a 0.05 level of significance, then our statistical decision is not to reject the first null hypothesis. So we will not reject the null hypothesis. Second, since the computed F value of 0.89 is less than the critical value of 3.26 at a 0.05 level of significance, the statistical decision is not to reject the second null hypothesis. Now, from these decisions, we will now have our conclusion. So there are also two conclusions. First is that since we did not reject the first null hypothesis, then we can say that there is no evidence of a difference in the average outputs between time periods. And second, since we also did not reject the second null hypothesis, we can also say or conclude that there is no evidence of difference in the average outputs among groups of workers. So for your assessment, you are to solve this given problem systematically, or you have to follow the step-by-step processes, and then this will be the problem with two questions. I hope that you were able to learn something from this topic about randomized block design for the analysis of the variance. And so I think that would be all. Thank you so much, and God bless everyone.